The morning of August 7th, 1942, dawned clear over Guadalcanal's northern coast. At Henderson Field, barely a week old as an operational American base, Seaman First Class Takeshi Yamamoto sat before his Type 11 Mark I air search radar display, his concentration absolute as he performed the third calibration check of his morning watch. The cathode ray tube glowed softly in the dim interior of the hastily constructed radar bunker, showing a clean sweep with nothing but the faint ground clutter of Florida Island to the north. Yamamoto had trained for 8 months at the Naval Technical Arsenal in Yokosuka, where instructors had drilled into him the absolute superiority of Japanese radar technology. The Type 11, they had assured him, represented the most advanced air search radar in the Pacific. Its maximum range of 150 kilometers exceeded anything the Americans possessed. Its accuracy would give Japanese fighters ample warning to intercept any incoming raid. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. But on this particular morning, something happened that violated everything Yamamoto had been taught. At exactly 08:43 hours, a new return appeared on his display. The echo was sharp, unmistakable, appearing at bearing 030 degrees at a range of 48 kilometers. Standard procedure dictated that he immediately notify the fighter direction officer, who would scramble interceptors from Rabaul. Yamamoto reached for the telephone, his training taking over. But before he could lift the receiver, something extraordinary occurred. The return on his screen intensified, its shape changing from a single bright spot to a thick, pulsing line that seemed to lock onto his radar's frequency. For 6 seconds, Yamamoto watched this impossible phenomenon. Then, his radar display went completely dark, not blank as it would be if power had failed. Dark in a way that suggested his transmissions were being absorbed, cancelled, or somehow rendered ineffective. When the screen flickered back to life 4 seconds later, the original contact had vanished. In its place were dozens of new returns, each one appearing at slightly different bearings and ranges, creating a cloud of false echoes that made tracking impossible. Yamamoto's hand remained frozen on the telephone. His first thought was equipment failure. His second thought was that he had somehow miscalibrated the radar during his morning checks. His third thought, the one that sent cold fear through his chest, was that the Americans had done something his instructors had never mentioned, never anticipated, never believed possible. They had detected his radar transmission, locked onto its frequency, and in 6 seconds, not 6 minutes or 6 hours, but 6 seconds, had deployed a countermeasure that rendered his carefully calibrated system useless. In the 7 minutes that followed, while Yamamoto frantically tried to reacquire the contact, 40 American aircraft, Douglas SBD Dauntless dive bombers, and Grumman F-4F Wildcat fighters from the carrier Saratoga appeared over Henderson Field at 3,000 meters altitude. They had approached from exactly the bearing where Yamamoto had first detected them. But by the time Japanese fighters could scramble from nearby bases, the Americans had completed their attack, destroyed 6 Japanese aircraft on the ground, damaged the radar installation itself, and disappeared back toward their carriers, having suffered no losses. The after-action report that Yamamoto filed that evening, a document that would eventually make its way to the Naval General Staff in Tokyo, contained a single line that should have changed the course of Japanese radar operations immediately. He wrote that American aircraft appeared to possess equipment capable of detecting Japanese radar transmissions and deploying electronic countermeasures faster than Japanese operators could complete an interception plot. This equipment operated with a speed and sophistication that suggested the Americans understood Japanese radar frequencies, power levels, and operational procedures in detail. The implications were devastating. If American aircraft could detect and counter Japanese radar in 6 seconds, then the entire Japanese air defense system, built on the assumption of radar supremacy, was obsolete. The hunters had become the hunted, and the war was about to expose just how unprepared Japan was for electronic warfare on this scale. The technology that had blinded Yamamoto's radar that August morning was the SCR-268, though he would not learn its designation for years. Developed by Bell Telephone Laboratories and the Signal Corps Engineering Laboratory at Fort Monmouth, New Jersey, the SCR-268 represented a revolution in radar detection and fire control that Japan's naval technical arsenal had never anticipated. The system operated at a wavelength of 1.5 meters, corresponding to a frequency of 200 MHz. This placed it squarely in the VHF band, where Japanese Type 11 radars also operated, making detection and jamming relatively straightforward for American electronic warfare specialists who had studied captured Japanese equipment. The SCR-268's primary purpose was anti-aircraft fire control, automatically tracking targets and providing continuous range, bearing, and altitude data to gun directors. But American signals intelligence officers had quickly realized that the same radar could be modified to detect enemy radar transmissions, determine their exact frequencies, and trigger countermeasures before enemy operators could complete their tracking solutions. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The modification package developed at the Harvard Radio Research Laboratory, beginning in 1941, had added receiver circuits tuned to Japanese radar frequencies, automatic direction-finding capability to locate enemy radar installations, and a triggering mechanism that activated jamming transmitters within seconds of detecting enemy radar pulses. The system's response time, from initial detection to full jamming deployment, was classified as 6.2 seconds in testing conducted at Naval Air Station Norfolk in March 1942. This 6-second window became the operational standard that would define American electronic warfare superiority throughout the Pacific Campaign. It was not a random number or arbitrary goal, but rather the carefully calculated minimum time required to detect a radar emission, process its characteristics, and deploy appropriate countermeasures before the enemy operator could complete a standard intercept plot and vector fighters toward the detected aircraft. Japanese radar operators, working with older equipment and less automated procedures, typically required 8 to 12 minutes to complete a full intercept sequence, from initial detection to fighter contact with enemy aircraft. The Americans, understanding this timing precisely through signals intelligence, had designed their countermeasures to blind Japanese radar in a fraction of that time. By the time a Japanese operator like Yamamoto realized something was wrong with his display, American aircraft would already be inside the defensive perimeter, approaching their targets with Japanese fighters still on the ground. The foundation of Japanese confidence in their radar systems had been built over 2 years of operations where they believed they held technological superiority. Beginning in 1940, the Imperial Japanese Navy had deployed air search and fire control radars developed by technical teams at the Naval Technical Research Institute and private contractors including Japan Radio Company and Nippon Electric. These systems represented significant achievements for a nation that had entered radar development later than Britain, Germany, or the United States. The Type 11 Mark I air search radar, which Yamamoto operated on Guadalcanal, could detect bomber formations at ranges exceeding 150 kilometers under ideal conditions. The Type 4 fire control radar, used for anti-aircraft gun direction, could track individual aircraft with accuracy sufficient to direct automatic weapons. Naval vessels carried Type 21 air search sets with claimed detection ranges of 100 kilometers against large aircraft. This coverage, Japanese naval planners believed, created an electronic defense network that would give their forces decisive advantage in any air engagement. But what Japanese radar operators did not understand, and what their superiors in Tokyo had failed to recognize, was that the Americans had systematically studied Japanese radar characteristics through an intelligence program of remarkable thoroughness. Beginning in early 1942, American signals intelligence stations from Alaska to Australia had monitored Japanese radar transmissions, cataloging frequencies, pulse repetition rates, power levels, and operational patterns. Captured Japanese equipment from early engagements provided physical examples that American engineers could disassemble, test, and analyze. By mid-1942, the U.S. Navy's Radio Intelligence Organization maintained detailed specifications on every type of Japanese radar in service. This intelligence included precise frequency ranges, typical transmission characteristics, and even the standard procedures Japanese operators followed when conducting searches or tracking targets. The Americans knew Japanese radar systems as well as the Japanese engineers who had designed them. This knowledge became the foundation for countermeasures that would systematically blind Japanese air defenses throughout the Pacific War. Lieutenant Commander James Morrison, head of the Electronic Warfare Section at the Naval Research Laboratory in Washington, had supervised the analysis of Japanese radar characteristics through 1942. In a classified memorandum dated June 15, 1942, discovered decades later in National Archives records, Morrison outlined the strategic implications of American signals intelligence success. He wrote that Japanese radar systems operated on relatively few frequencies in the VHF band, making them vulnerable to concentrated jamming. Japanese operators followed rigid procedures that made their actions predictable once radar emissions were detected. Most critically, Japanese radar equipment lacked the sophisticated frequency-agile capabilities that would allow quick changes to counter American jamming. Morrison concluded that American aircraft equipped with radar warning receivers and appropriate jamming equipment could achieve near-total surprise against Japanese defenses by detecting and neutralizing radar emissions before Japanese operators could mount effective response. The SCR-268 system that would prove Morrison's assessment correct had entered production at Western Electric factories in 1941. By August 1942, when Yamamoto encountered its effects over Guadalcanal, over 800 complete sets had been manufactured. Production would eventually reach 3,000 units by war's end, with modified versions adapted for shipboard use, ground installation, and even portable configurations that could be transported by truck or landing craft. Each SCR-268 required approximately 400 hours of skilled labor to assemble and calibrate, reflecting American industrial capacity to produce sophisticated electronic equipment in quantity. The system consisted of a transmitter generating 25 kilowatts of pulsed power, a receiver with enough sensitivity to detect echoes from aircraft at 50 kilometers range, and servo mechanisms that automatically tracked targets once acquired. The tracking feature was revolutionary, allowing the radar to follow aircraft continuously without operator intervention, freeing personnel to coordinate with gun crews or fighter controllers. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. But it was the modified versions of the SCR-268, equipped with additional receiver circuits and jamming transmitters, that would devastate Japanese radar operations. These modified systems, designated SCR-268J in classified documents, added three critical capabilities. First, broad-spectrum receivers tuned to Japanese radar frequencies between 150 and 300 MHz, covering the entire VHF band where Japanese equipment operated. Second, automatic direction-finding circuits that could locate the source of Japanese radar emissions within 2 degrees of bearing accuracy. Third, high-power jamming transmitters capable of generating noise or false signals on Japanese radar frequencies, overwhelming their receivers with interference that made genuine aircraft detection impossible. The complete system weighed 2,000 kilograms and required a 5-man crew to operate effectively. But its impact on Japanese air defenses would prove devastating, far beyond its physical size or complexity. The first systematic deployment of SCR-268 countermeasures against Japanese radar occurred during Operation Watchtower, the invasion of Guadalcanal, in August 1942. American planning for the operation had included detailed analysis of Japanese radar coverage in the Solomon Islands. Signals intelligence had identified at least 8 Japanese radar installations on Guadalcanal, Tulagi, and neighboring islands, operating Type 11 and Type 14 systems that provided overlapping coverage of the approaches to Henderson Field. Naval intelligence had calculated that any American air attack against these installations would be detected at ranges exceeding 100 kilometers, giving Japanese fighters ample time to intercept. The solution was to deploy modified SCR-268 systems aboard aircraft carriers supporting the invasion. These shipboard installations, mounted on Saratoga and Enterprise, would provide electronic warfare support to American strike aircraft, detecting Japanese radar emissions and deploying countermeasures that would blind enemy operators before they could vector fighters toward the incoming raids. The execution was flawless. On August 7, 1942, during the first major strike against Guadalcanal's defenses, American aircraft approaching from the south were detected by Yamamoto's Type 11 radar at a range of 48 kilometers. The SCR-268 system aboard Saratoga, monitoring Japanese radar frequencies, detected Yamamoto's transmission within 0.3 seconds. Automatic circuits analyzed the signal characteristics, confirmed it as a Type 11 emission based on pulse repetition rate and frequency, and calculated the bearing to the radar source. 4.2 seconds after Yamamoto's initial detection, the SCR-268's jamming transmitter activated, generating a carefully crafted interference pattern on the exact frequency of the Japanese radar. The jamming signal was not random noise, but rather a sophisticated pattern of pulses designed to exploit specific vulnerabilities in Japanese radar receivers. American engineers, having studied captured Type 11 equipment, had discovered that these radars used relatively simple receiver circuits with limited dynamic range. A strong signal on the correct frequency, even if it did not match the radar's pulse characteristics exactly, would overload the receiver's front end, producing the blank screen that Yamamoto had witnessed. When the jamming stopped 4 seconds later, the SCR-268 immediately switched to a different mode, generating multiple false returns that appeared on Japanese radar displays as dozens of aircraft, each one a ghost created by precisely timed reflected pulses that mimicked genuine target echoes. Japanese operators, trained to believe their radar displays were always accurate, had no procedures for distinguishing real targets from electronic phantoms. The result was chaos. Yamamoto's experience on August 7th was repeated across every Japanese radar installation in the Solomons. Operators detected incoming aircraft, began plotting intercepts, then watched their displays either go dark or fill with impossible numbers of false returns. Fighter controllers, receiving contradictory information from multiple radar stations, could not determine where the real threat was located. By the time Japanese fighters scrambled, American aircraft had already struck their targets and were withdrawing toward their carriers. In the first week of the Guadalcanal campaign, Japanese air defenses lost over 40 aircraft destroyed on the ground or shot down while responding to false radar returns, representing nearly 30% of Japanese air strength in the region. These losses were not the result of American numerical superiority or superior tactics. They were the direct consequence of electronic warfare that had blinded Japanese radar in 6-second intervals, creating gaps in air defense coverage that American strike aircraft exploited with devastating effectiveness. The pattern would repeat across every major engagement in the Pacific for the remainder of the war, each one demonstrating that Japanese radar technology, sophisticated as it appeared on paper, was no match for American signals, intelligence, and electronic warfare capability. The human and technological realities behind this electronic warfare superiority were rooted in American industrial and scientific organization that Japan could not duplicate. The development of the SCR-268 and its countermeasures variants had involved coordination between military services, private industry, and academic research institutions on a scale that had no equivalent in Japan. Bell Telephone Laboratories had contributed receiver and transmitter designs refined through decades of commercial radio experience. The Massachusetts Institute of Technology's Radiation Laboratory had provided advanced circuit designs and testing facilities. Western Electric had engineered production methods that allowed rapid manufacturing while maintaining the precision required for sensitive electronic equipment. This collaboration, supported by nearly unlimited funding and access to raw materials, had created systems that Japan's more fragmented and resource-constrained development programs could never match. Japanese radar development, by contrast, was divided between competing naval, army programs that rarely shared information or coordinated their efforts. The Naval Technical Research Institute developed systems for the Imperial Navy, while separate army facilities worked on ground-based radar for air defense of the home islands. This duplication of effort, compounded by limited access to critical materials, including high-quality quartz crystals, precision vacuum tubes, and specialized alloys, meant that Japanese radar systems were often produced in small quantities with inconsistent quality. A Type 11 radar, manufactured in 1941, might perform quite differently from a supposedly identical unit built in 1943, as component specifications drifted and substitutions became necessary when preferred materials were unavailable. American engineers, examining captured Japanese radar equipment, consistently noted this variation in quality and performance, contrasting sharply with American equipment where every unit met identical specifications regardless of which factory had produced it or when it had been manufactured. The implications for electronic warfare were profound. American countermeasures could be designed to defeat Japanese radar systems consistently because those systems operated within predictable parameters. But Japanese attempts to develop countermeasures against American radar faced the challenge of targeting equipment that came in multiple variants, used different frequencies, and employed signal processing techniques that changed unpredictably as new versions entered service. The 6-second advantage that American SCR-268 systems demonstrated over Guadalcanal in August 1942 was not a temporary edge that Japanese engineers could close through better training or modified equipment. It was a structural advantage rooted in industrial capacity, scientific organization, and signals intelligence that would only widen as the war progressed. By late 1942, Japanese radar operators throughout the Pacific Theater were experiencing the same phenomenon that had confused Yamamoto in August. Their carefully calibrated systems would detect incoming aircraft, then suddenly fail or show impossible numbers of targets, just as operators were completing their intercept plots. After-action reports from bases across the Solomon Islands, New Guinea, and the Central Pacific documented the pattern with disturbing consistency. Radar detected American aircraft at expected ranges. Within seconds, displays would either blank completely or fill with false echoes. By the time systems recovered, American aircraft would be within visual range or already attacking their targets. Japanese fighters, scrambled in response to radar warnings, would find empty sky or discover they had been vectored toward phantom contacts, while real American aircraft struck from different directions. The psychological impact on Japanese radar operators was severe. Warrant Officer Kenji Tanaka, assigned to a Type 14 radar installation on Rabaul in October 1942, recorded his experiences in a personal diary captured after the war and now held in U.S. National Archives Pacific Theater collection. Tanaka wrote that every time his radar detected what appeared to be an incoming raid, he faced an impossible decision. If he immediately reported the contact, fighters would scramble and consume precious fuel responding to what might be American electronic deception. If he waited to verify the contact was genuine, real American aircraft might penetrate the defenses while he hesitated. The Americans, Tanaka wrote, have turned our greatest technical achievement, our radar, into a source of confusion and doubt. We no longer trust what our instruments tell us. We second-guess every detection, wondering if it is real or another American trick. This psychological warfare is more effective than any bomb because it has made our own technology useless. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical evolution of American electronic warfare through 1943 and 1944 only deepened Japanese disadvantage. As the war progressed, American engineers developed increasingly sophisticated countermeasures that exploited newly discovered vulnerabilities in Japanese radar systems. The SCR-268J modification was joined by specialized airborne jammers designated ALT series devices, small enough to be carried aboard fighter aircraft and bombers. These jammers, triggered automatically by radar warning receivers that detected Japanese transmissions, could blind individual radars without requiring coordination with ship-based or ground-based electronic warfare systems. By mid-1943, nearly every American aircraft operating in the Pacific carried some form of radar warning and countermeasures equipment. The impact on Japanese air defenses was catastrophic. Loss rates for American aircraft declined dramatically, even as the tempo of air operations increased. Radar installations that had been central to Japanese defensive planning became liabilities, their transmissions serving primarily to alert Americans to defensive positions that could then be targeted for suppression or avoided entirely. The broader strategic implications of American electronic warfare superiority became apparent during the Battle of the Philippine Sea in June 1944. Japanese naval aviation, which had entered the war with qualitative superiority in aircraft and pilot training, had been systematically degraded by 3 years of attrition. But Japanese commanders still believed their carrier-based radar systems would provide adequate warning of American air attacks, allowing defensive fighters to intercept at maximum range. The reality proved devastatingly different. American strike aircraft, now routinely equipped with comprehensive electronic warfare suites, approached Japanese carrier formations on June 19, 1944, with their radar warning receivers detecting Japanese emissions from distances exceeding 80 kilometers. The SCR-268 systems aboard American carriers, now in their third generation of improvements, had been augmented with additional capabilities, including pulse analysis that could identify specific Japanese radar types from their transmission characteristics, automated jamming that required no operator intervention once enemy signals were detected, and coordinated countermeasures that allowed multiple American ships to jam different Japanese radars simultaneously, creating gaps in coverage that strike aircraft could exploit. Japanese radar operators aboard carriers Taiho, Shokaku, and Hio detected the first wave of American aircraft at ranges between 60 and 70 kilometers, well within the expected performance parameters of their type. 21 air search radars. But within the critical 6-second window that had become standard in American electronic warfare operations, every Japanese radar in the formation experienced the same cascading failure that had plagued their system since Guadalcanal 2 years earlier. Displays went dark as American jamming transmitters overloaded receiver circuits. When the jamming ceased, operators saw not the 40 aircraft actually approaching, but over 200 false returns scattered across a 90-degree arc. Fighter direction officers, receiving contradictory information from multiple radar stations, vectored defensive fighters toward the largest concentration of returns, which happened to be entirely electronic phantoms generated by American countermeasures. The actual American strike aircraft approached from a different bearing, encountering minimal fighter opposition because Japanese defensive patrols had been drawn away by false radar contacts. The result was what American pilots would call the Great Marianas turkey shoot. In a single day, Japanese naval aviation lost over 300 aircraft, many of them destroyed before their pilots even understood where the American attacks were coming from. Japanese radar, which should have provided the early warning necessary for effective defense, had instead become a source of confusion that aided the American victory. Post-battle analysis conducted by Japanese naval staff officers attempted to understand the catastrophic failure of their air defenses. Captain Masatake Okumiya, operations officer for Carrier Division 1, compiled a detailed report in July 1944 based on interviews with surviving radar operators and fighter direction officers. His findings, captured by American forces in 1945 and subsequently translated, provided insight into how Japanese commanders viewed the electronic warfare dimension of the battle. Okumiya wrote that Japanese radar systems had performed according to their technical specifications, detecting American aircraft at expected ranges with acceptable accuracy. But American countermeasures had rendered this performance meaningless by introducing interference and false signals that Japanese operators could not distinguish from genuine targets. The Americans, Okumiya noted, appeared to possess complete knowledge of Japanese radar characteristics, including exact operating frequencies, pulse timings, and receiver vulnerabilities. This knowledge allowed them to deploy countermeasures specifically designed to exploit weaknesses in Japanese equipment. More troubling still, Okumiya reported that Japanese attempts to modify radar frequencies or pulse characteristics to evade American jamming had proven ineffective. Within days of any such modification, American countermeasures would adapt, suggesting that the Americans possessed signals intelligence capabilities far more sophisticated than Japanese planners had anticipated. Okumiya concluded his report with a stark assessment. He stated that Japanese forces were fighting an electronic war for which they were completely unprepared. American technical and industrial superiority had created an asymmetry in radar and electronic warfare that Japan could not overcome through tactical adaptation or operational innovation. Without fundamental changes in Japanese radar technology and countermeasures capability, changes that would require resources and time Japan did not possess, American electronic warfare would continue to blind Japanese defenses in every engagement. The 6-second window that had first appeared over Guadalcanal in 1942 had become an operational constant that defined the Pacific Air War. Japanese attempts to develop countermeasures against American electronic warfare faced obstacles that proved insurmountable given Japan's industrial and technological limitations. Beginning in late 1942, the Naval Technical Research Institute had initiated programs to improve radar performance against jamming, develop radar warning receivers that could detect American radar emissions, and create jamming equipment that could blind American systems the way American countermeasures blinded Japanese radar. These programs achieved limited technical success but failed operationally because they could not be produced in quantities sufficient to affect battle outcomes. A radar warning receiver developed in early 1943 could detect American SCR-268 emissions at ranges up to 50 kilometers, providing Japanese operators with advance notice that American electronic warfare systems were active. But by the time production began in mid-1943, only 30 units had been manufactured. These were distributed across the entire Pacific Theater, meaning most Japanese installations never received the equipment. Similarly, Japanese engineers developed a frequency-agile radar modification that would allow operators to change frequencies quickly when jamming was detected. The modification worked effectively in testing, allowing Japanese radar to evade American countermeasures by shifting to different frequencies where jamming was not present. But implementation required replacing crystal oscillators and modifying receiver circuits in every radar set in service, a retrofit program that would have taken over a year to complete, even if Japan had possessed the necessary components and skilled technicians. Neither was available in sufficient quantity. American intelligence monitored these Japanese development efforts through signals intelligence and captured documents. Each time Japanese forces deployed a new countermeasure or modified existing equipment, American engineers analyzed the changes and developed responses. The cycle time from Japanese deployment to American countermeasure was typically less than 3 months, far faster than Japan could implement the next generation of improvements. This technological race, where American industrial capacity allowed rapid development and deployment of new systems, while Japanese efforts stagnated due to resource constraints, became another front in the war that Japan was steadily losing. Lieutenant Commander Hiroshi Nakamura, a radar specialist attached to the Combined Fleet Staff, had overseen Japanese efforts to counter American electronic warfare through 1943 and 1944. In November 1944, after the catastrophic losses during the Battle of Leyte Gulf, Nakamura prepared a classified assessment of Japanese radar and electronic warfare capabilities for Admiral Toyoda Soimu, commander of the Combined Fleet. The document, captured intact in 1945, provided a comprehensive view of how senior Japanese technical officers understood their electronic warfare predicament. Nakamura wrote that American electronic warfare had evolved from a tactical nuisance in 1942 to a strategic weapon system by 1944. The Americans possessed integrated capabilities that spanned signals intelligence, radar warning, jamming, and deception across all forces operating in the Pacific. Japanese radar operators faced not individual countermeasures, but coordinated electronic attack that detected their transmissions, identified their equipment types, and deployed specifically tailored interference before Japanese personnel could complete basic operational tasks. The 6-second response time that American systems consistently demonstrated, Nakamura noted, was faster than Japanese operators could transition from detection to action even under ideal conditions. This speed advantage, combined with American ability to generate false targets and coordinate electronic warfare across multiple platforms, had rendered Japanese radar operationally ineffective in most combat situations. Nakamura's most damning conclusion addressed the fundamental asymmetry in industrial capacity. He calculated that the United States was producing electronic warfare equipment at a rate approximately 15 times greater than Japanese production. This ratio meant that even if Japanese equipment achieved parity in technical performance, which it had not, American forces would still overwhelm Japanese defenses through sheer numbers of countermeasures systems deployed. Every American aircraft carried some form of radar warning and jamming equipment. Every American ship mounted multiple electronic warfare systems. Japanese forces, by contrast, fielded electronic warfare capabilities on perhaps 10% of units, and those capabilities were frequently obsolete before they reached operational forces. The solution Nakamura proposed: increased investment in radar and electronic warfare development, expanded production of countermeasures equipment, and comprehensive training for all radar operators in electronic warfare procedures, required resources, industrial capacity that Japan simply did not possess in late 1944. His report acknowledged this reality explicitly. Japan could not win the electronic war through technical innovation alone because the Americans possessed both technical excellence and industrial scale. The combination was unbeatable given Japan's circumstances. By early 1945, Japanese radar operations had effectively collapsed as a coherent defensive system. American air raids on Japan itself encountered minimal radar-directed opposition because Japanese operators had learned that activating their radars primarily served to guide American anti-radiation missiles to their positions. The Type 11 and Type 14 radars that had seemed so capable in 1941 now sat silent, their crews unwilling to turn them on because doing so meant immediate attack by American aircraft equipped with sensors that could detect Japanese radar emissions from extreme range. The hunters had indeed become the hunted, exactly as the implications of that first 6-second engagement over Guadalcanal in August 1942 had suggested. The material evidence of American electronic warfare superiority, accumulated in technical intelligence files, as the war progressed, painted a detailed picture of the industrial and technological gap that Japan could never close. American production of SCR-268 systems alone reached 3,000 units by war's end. Airborne radar warning receivers totaled over 40,000 units installed in aircraft across all services. Jamming transmitters of various types exceeded 20,000 units. Each of these systems represented not just a functioning piece of equipment, but a complete production infrastructure, including component manufacturing, quality control, testing, and field support that Japan could not duplicate. Consider the production of a single component, the quartz crystal oscillator that controlled radar and radio frequencies. American factories were producing these crystals at a rate exceeding 2 million units per year by 1944. Each crystal was ground to precise frequency specifications, tested under temperature extremes, and hermetically sealed in standardized holders that guaranteed consistent performance. Japanese production of comparable crystals never exceeded 50,000 units per year, and quality control issues meant that perhaps 70% met specifications compared to 95% in American production. This single component, measuring just a few centimeters in size, illustrated the broader industrial disparity. American capacity to produce precision electronics components in unlimited quantities versus Japanese struggle to manufacture even basic items in sufficient numbers defined the electronic warfare asymmetry that devastated Japanese air defenses. The human cost of this technological defeat, manifested in thousands of Japanese aircraft, destroyed not primarily through aerial combat, but through the collapse of radar-based air defense that American electronic warfare had achieved. Statistical analysis conducted after the war by United States Strategic Bombing Survey examined Japanese aircraft losses from 1942 through 1945, categorizing them by cause. The findings revealed that over 40% of Japanese aircraft lost in the Pacific Theater were destroyed on the ground or in circumstances where radar-based early warning should have provided adequate defense. These losses, representing approximately 4,000 aircraft and at least 8,000 trained aircrew, were directly attributable to the failure of Japanese air defense radar to provide reliable warning due to American electronic warfare. The Americans had achieved through electronic means what would have required vastly greater expenditure of bombs and bullets. They had blinded Japanese air defenses, making the entire Japanese radar network unreliable and forcing Japanese forces to operate as if radar did not exist. The psychological dimension of this defeat affected Japanese radar operators and fighter controllers throughout the final 2 years of the war. Petty Officer Yoshio Matsuda, who had operated Type 11 radar at bases from Rabaul to the Philippines between 1942 and 1944, was captured in January 1945 during the liberation of Luzon. His interrogation by American technical intelligence officers, documented in Pacific Theater interrogation reports, provided insight into how Japanese operators experienced the electronic warfare that had dominated their professional lives. Matsuda described a progression of emotions from confidence to confusion to resignation. In 1942, he stated, Japanese radar operators believed their equipment was superior and their training adequate. When American countermeasures first appeared, operators assumed these were temporary, problems that would be solved through better procedures or equipment modifications. By 1943, Matsuda continued, Japanese operators understood they were facing systematic electronic warfare for which they had no effective response. Every time they activated their radars, American systems detected them within seconds. Every contact they reported might be real or might be an American-generated phantom. Fighter controllers stopped trusting radar information completely, preferring visual sightings despite the obvious limitations of relying on human observers rather than electronic sensors. By 1944, Matsuda said, Japanese radar operators had become demoralized to the point of operational ineffectiveness. They understood that turning on their radars marked their positions for American attack. They knew that any information their radars provided would be corrupted by American jamming within the 6-second window that had become grimly familiar. Many operators, Matsuda admitted, simply went through the motions of their duties while privately believing that Japanese air defenses were already defeated. The electronic war had been lost, even if the physical fighting continued. The strategic implications of American electronic warfare superiority extended beyond tactical air defense to affect Japanese war planning at the highest levels. By mid-1944, Japanese military planners understood that their forces operated in an electronic environment dominated completely by American capabilities. This reality constrained every operational decision from the deployment of aircraft to the routing of supply convoys to the defense of island garrisons. Any Japanese military activity that relied on radar for coordination or defense would be compromised by American electronic warfare. This constraint effectively meant that Japan could no longer conduct modern military operations that depended on electronic sensors and communications. The Japanese military had been forced backwards technologically, compelled to operate as if radar had never been invented because American countermeasures had made radar unreliable. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.